In the last video, we saw how to do integrals on rectangular on rectangles that are taken over rectangles. But many of the integrals are not going to be on rectangles; they're going to be on general regions. So we want to address that. From a formal point of view, theoretical point of view, we want to go from one to another. Uh, and the question is, how do we define it? If you have a general region, so let's put a rectangle first, but just for reference, and we have just some kind of general region, and we want to integrate a surface over this region. So the surface is on top of this, something like that, and then each point corresponds to a point from here. So there's the front and then the back. And so we want to obtain the integral of this f of xy with respect to the area on the bottom. The way we, from a theoretical point of view, move from rectangles to non-rectangles is by thinking, well, we know how to do a rectangle, and the regions we are going to be working are going to be bounded. That means they're going to be finite. They're not going to go on forever. So that means there's going to be some rectangle that will have that region inside of that rectangle. And so from a theoretical point of view, the way we define the double integral is by simply making up a new function. So set g of xy to be equal to, let's label this region as R, as f of xy if xy is in the region and 0 otherwise. Yep. So the function may be only this portion here. This may be the function, but we can always embed this function into another function in which, if we're in the region, we have that, and if we're not in the region, we have 0. So really, this turns out to be, we can think of this as an integral over a rectangle, which we have defined in the previous video, in the video 51801. But that is only theoretical. That won't tell us how to actually obtain a solution. So this is just a theoretical comment. How do we actually go about it? We will split regions into two categories. The first category will be a region that is non-rectangular with a y variable boundary. So we're going to have two cases. Okay, we will have the y variable boundary case and the x, so let's put a bullet here, x variable boundary case. Yep. So the y variable boundary case for the region is, so let me see how we can abbreviate this. So y variable boundary case, x variable boundary case, okay, of a region. So the y variable boundary case on the xy axis, standard one looks like this. We have the x is fixed from, say, A to B, but the y is not fixed. That's why it is a y variable boundary case. So perhaps we can have something like this. And we're going to label this bottom boundary instead of C and D, as we did with the rectangular regions, we're going to go from F1 of X to F2 of X. So we're going to assume we're going to include the restriction that F2 will be above F1. Okay, so we go, the way you can tell you have this kind of region is because the two sides on the left and on the right are going to be straight lines or parts of straight lines. I was going to say segments, but we could have a part of a straight line that is so small that it turns out to be a point. That would be okay. Yeah. So if this side is a point or that side is a point, we're still good. We're okay. Now, the X variable boundary case on the X, so these are the region, this is just the generic region R. On the XY axis or XY plane, would look more typically like this. The top and the bottom is going to be constant, C, D, and the left and the right could vary. So the left will be a function of Y. So we will label this as G1 of Y as opposed to some function of X. And this, the right side, the right boundary would be G2 of Y. Yeah. Most of the time, we're going to be looking at this from the top, a top view, but watch out because these graphs, these regions, so this is a region, just a generic region R, will look somewhat different if we look at this in a three-dimensional picture. That was a little bit too long, but yeah, let's do this. There we go. So in this case, the X is constant. So this straight line, I'm going to try to transfer this into a three-dimensional picture. So this X is constant. That means that this X, which would be A, would be constant. And this X would be constant. So again, constant. And the shape of the sides, the shapes of the up and down boundary are non-constant. So this, we could have some kind of curve and some kind of curve here. So watch out because this picture, this is the X, Y, Z axis. This picture that has the vertical straight lines will, when you transfer it down to here, will have horizontal straight lines. So we would have going from A to B, and then from, so this, the bottom would be this one, F1, and the top would be F2. Yeah, so top and bottom are now relative terms, you know, so this is the bottom, but when you put it here, the way we see it is gonna be on our left. So bottom, I'm reading a book, Ender's Game. I haven't finished it yet, but I'm impressed. I believe that it's an old book, and one of the things they do is the main character is that he's very good at figuring out where the bottom is, and if he needs to reposition himself to change the bottom, you know, then he does it very, very efficiently, very quickly, without too many issues. So that makes me think of this, or this makes me think of that. Either way, we have to have the ability to be able to tell, okay, in this picture, the bottom is here, but in this picture, the bottom is that. Bottom and top is relative. So just be aware of that relative way of thinking. So once you have this, it is easy to picture the other one. So this is a generic picture. Now, of a region R. And then the surface is going to be up here somewhere. The surface is going to be up here. I don't want to do too much with this. The main thing here is that this is straight, so CD. This would be G1 and this would be G2 because the bottom is closer to the y-axis and versus the top. Yeah. So just be aware of that. And then towards the end of this video, I'm going to show you some pictures where you could see them in both ways. We can see a region in two. That could be this one or this one, or actually that could be both of them. Yeah, I might just as well continue with this idea real quick. If you have y variable boundary case, again, you could have some kind of curve, two straight lines, but these lines don't have to be long or short. They could be a point. So if you end up with something like this, that is still the case of the y variable boundary, because the left is straight. So we go from A to B, and then the height changes. That's what we mean by the y variable. The y boundary changes, just like this boundaries, this changes across as we go from A to B. And you can have the case where we have a point and a point. So one side could be a segment and one side a point. I guess I didn't draw the case where you have a point on the left and a segment, not a point on the right, a segment that would be this reversed, still maintaining the A on the left and the B on the right. Or you can have this. We have a point and then a variable y. So all of this, A, B. All of those cases are cases of y variable boundary case, x variable boundary case. Again, so we go from C to D, assuming that we are looking at the picture from the top, not a three-dimensional picture, because again, that changes things around. Then we have some kind of curve here, not necessarily the same curve, but something else. But one of those could be a point. So you could have I don't want to make it too fancy, but there, that could be a picture from C to D. So again, what happens here is that this varies, going up and down is pretty much the same, but this is varying. And so is this, those distances are varying or could vary. All right, but then this picture, I'm kind of copying the same picture, could go from C to D, and the axes are varying. So I guess I lied. I said that I was going to show you this at the end of the video, but then I realized I changed my mind. As long as we were talking about the different kinds of regions, I just as well show you this. All right. Yeah. So what we are going to do is double integrals. So a double integral of, whoops, I meant f of x, y with respect to the area over a region. Now, if we have a region of this kind, we're going to change that into an iterated integral from A to B on the axis, but on the y's, we're going to have a variable boundary. The bottom changes. So we're going to go from f1 of x, where this would be, so the bottom will always be f1 for us, f1, 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 and the top will be f2, f2 of x. That's a little confusing. I shouldn't have used f's. So I'm using F1 and F2 for the boundaries, and I'm also using F without a subindex for the surface. Please do not, I just realized I did that, but it's okay because we're using indexes. So technically speaking, those are three different functions. So let me put this on this perspective. So we have F1 boundary, F2 boundary, and F would be the surface going on up here. So please, even though I'm using the same lowercase f, because I'm putting indexes, and because I'm using only x, that is making them distinguishable. It's unfortunate that I did use the same little f, lowercase f, for the three, but those are three different things. All right. And then we are integrating the surface with respect to y first and with respect to x. So this is the way we set up a double integral if we are in the y variable boundary case. Y a variable boundary case. Different books will not have a long name like that. They will call them perhaps, I don't know, case one or case two or case one or case two, and that's all right. I'm just choosing to call them what they are: y variable boundary. The same integral. So I'm going to copy this down again. All right. If you are in one of those cases, can be written as the integral from c to d of the integral of from g1 of y to g2 of y. So g1 is going to be the smallest, which in this case, because we are thinking of these pictures on the xy plane, the smallest is going to be on the left, and the larger g is going to be on the right. And this picture is away from us because that, well, but then again, all of this is relative. If this region was on the other side of the y-axis, then g, oh yeah, no, never mind. G1 will still be the one that is farther away, because this would be the top and the bottom, regardless of whether this is in front of the y-axis or behind the y-axis. Yeah, so it's always going to be the same. G1 is going to be in this picture on the left, and G2 is going to be on the right. G1, G2, G1, G2 of y. Yep. On these cases, we have F1 on the bottom, F2 on the top, F2 on the top, F2 on the top. And then you may be thinking, wait a minute, so F2 is the same as G1. Yes and no, not really, because G is a function of y, while F is a function of x. F2 is a function of x. We're going to do an example that is going to combine the two. Same function, xy, dx, dy. So this is the proper setup if you have a region of this. Some regions, like this one, can be seen in two different views. In that case, well, you can do it either way. And one may be easier than the other. And we many times cannot tell in advance which one will be easier than the other. So this is an x variable boundary case. Yep. So let's do an example. Let's do example 1. Okay. Evaluate the double integral of x squared plus y squared with respect to the area over the region R, where R is equal to the set of x, y points on the plane, R squared, such that, okay, y is going to be between half x and a third x plus 4, while x, so comma, is between 0 and 6. Close. Okay. So we have two boundaries, variable boundaries for y. Y is not between fixed numbers such as in x. X is between 0 and 6. So that means we have a region where the y is variable and the x is going to be fixed. So in this case, I wanted to have a little nicer of a graph, so I drew the graph ahead of time. Here it is. So this is the y-axis, the x-axis, and this is this is the x-axis, y-axis. That is the origin. And so 1/2 x looks like this from 0 to 6. We're going to assume that each one of those squares is a 1 by 1 square. So this goes from 0 to 6. For instance, this point up here will be 6, 3, which makes sense. This is 0, 0, because when you plug in 6, 1/2 times 6 gives you 3 as an output. This point up here is going to be 6, 6. Yep, and this, I wrote these terms differently. 1/3 x plus 4, 4 plus 1/3 x, same thing. So this is the line. This is the line. And of course, the two lines will go on and eventually will cross each other, and they'll get away from each other here because the slopes are different, so they're not parallel. So this is not a parallelogram because this has a slope of 1/3, that line on top. This line on the bottom has a slope of 1/2. So even though they seem a little bit parallel, they're not. They're definitely not parallel. And however, the left side and the right side are parallel because we have that x goes from 0 to 6. Those are fixed numbers, 0, 6. So this is a y variable boundary case. Yeah, those heights keep changing. So this is long. How long is this? We can actually count 1, 2, 3, 4. So this is 4 units tall, this side, this segment, while this segment is 1, 2, 3, 3 units tall. So this is changing uniformly. So we go from 4 down to 3. And we want to find the integral. Okay, so the reason why I have this picture is because my picture here is not going to be, once we implement 3 dimensions, that's not going to be as smooth. So we have something like this from the origin, a little, there you go. See, that's already not that great, but this quadrilateral is supposed to be this one. So there's, as we go away from the origin, there's a gap. This is the gap. Yep. So we go from 0 to 6. This number will be 6, and then that number will be 6 also. And we are integrating this paraboloid. So the paraboloid, as you know, goes this way. So this point is attached to that. This is attached to a point here. This is attached to a point there. This one is going to be attached to a point farther up on the paraboloid. So we're going to integrate and obtain, since the function is always positive, we're going to obtain the volume under the paraboloid, but above this quadrilateral. Yep. So there's going to be a paraboloid here that opens up, and we want to find the volume above this quadrilateral, but below the paraboloid. Good. So let me just draw another picture. So we got again, some kind of quadrilateral. And yeah, this picture is not, I'm just trying to draw a little nicer of a picture. Yeah, never mind. Let's just continue with this. Okay, so period. So what we want to do is find the double integral r x squared plus y squared dA. And as I mentioned on the previous sheet, we're going to go from 0 to 6 and the two functions. So this is the integral from 0 to 6, integral from the bottom function, which is half x, to the top, third x plus 4 of x squared plus y squared. We're going to integrate first with respect to y, because that's what's varying, and then with respect to x. Remember, this is an iterated integral, so we went from a double integral to an iterated integral. And then we evaluate the iterated integral as we know, except that those two are not fixed numbers, they are variables themselves. So we go ahead and the integral from 0 to 6, we're integrating with respect to y. So x is a constant, x squared y plus y cubed over 3 from half x to a third x plus 4. We're going to integrate that with respect to x. So the integration with respect to x is waiting while we figure this out. Okay, so that is from 0 to 6, x squared. And then we're going to plug that on top. Well, 1/3 x plus 4. We're going to plug that in for y plus 1/3 x plus 4 cubed over 3. Yep, over 3. And then we're going to subtract. So this is getting long enough that I need to use a second line for this computation. We're going to subtract x squared times half x. And then we also have to subtract half x cubed over 3, close the parenthesis. And then what I'm going to do is simplify this before we do the evaluate this integral. Now, this is an integral from Calculus 1. It's an ugly integral, but it is still an integral from Calc 1. Yes. I'm going to ask my students to evaluate this integral algebraically. Some instructors, some teachers will say, well, once you set it up, you can punch it into, graphing calculators such as this one, and then get the result, and that would be okay. That is their prerogative. Nothing wrong with that necessarily. No, I don't think so. My students, I prefer that my students do this algebraically. Now, you can always double check your answer, but there are some skills, algebraic skills, that we need to maintain, retain as we do this. There are not algebraic skills and some other skills that I think students develop. This is my page number. I'm on page 3. As we do this algebraically. Does that mean that I'm a better or worse instructor? I don't think so. It is just different than other instructors. Other instructors will want you to get to this point. Once you get to this point, they think, well, just punch it into the calculator. A graphing calculator, there is no point on crunching the numbers when we have a very, very powerful calculator. And I don't think there is necessarily anything wrong with that. It is just different. All right, 0 to 6. So there's a bunch of algebra we have to compute here. You know, as I'm looking at this, x squared, we can factor out the x squared and then simplify this. This is 1/3 of x, and then we're going to take away a half of x. So 1/3 minus 1/2. I've done that so many times, I know what it is. It is negative 1/6 of x. So again, 1/3 x minus 1/2 x. After factoring out the x squared is negative 1/6. And then we still have the 4. All right. Plus, those two have a 1/3, which I'm going to factor out, 1/3 parenthesis, and then I'm going to start foiling that out. Yeah, this cubic has to be foiled. If you are not very familiar with foiling a cubic, by the way, I'm using the word foil, which is technically incorrect because that is used only for two binomials that we are multiplying together. These are three binomials. They're the same binomial, but still three of them. So technically speaking, we're not foiling. Maybe we're foiling for two of them, but then we got to multiply that by 1/3 x plus 4. Anyway, so if you're not familiar, practice that. That will take you a little bit. So just multiplying this with itself. So we have three of them. We end up with 1/27 x cubed. All right. And then plus 1/9. But then we multiply by 3. So that's 1/3 times 4. So that is 4/3 x squared plus 1/3, which we multiply by 3. So that gets rid of the 3. And then 16x plus 64. Yep. So I got 4 terms by multiplying this out. You know, so if you should end up with those 4, you might want to pause the video and actually fold that out on a different piece of paper to make sure you actually end up with this. So all I'm doing is multiplying this 1/3 x plus 4 times 1/3 x plus 4 times 1/3 x plus 4, and then obtaining this. And then we're subtracting this quantity. So I might just as well write it in this polynomial because I'm factoring out the 1/3 from those two. Just like in this two, I factor out the x squared. So we have 1/8 x cubed. So minus 1/8 x cubed. Close the parenthesis. And then we still have dx. So, we got to close another parenthesis. So I'm going to continue here. So this parenthesis closes this one. This one has not been closed, so it's kind of awkward, but I'm going to close the parenthesis, the very first one, and then dx. So this line, this integral, original integral, which was written in one line, here it is written in 2 lines, and now I'm writing it in 3 lines because it's just getting long. Okay, so let's distribute the x squared. So this is the integral from 0 to 6 of negative 1/6 x cubed plus 4x squared. And then down here, I'm going to do 2 things. I'm going to simplify those 2. And then we're going to multiply by 1/3. You know what? I'm going to simplify those real quick on a different piece of paper. So we have 1/27, 1/27. And then this x cubed is 1/8. So we do 1/8. The subtraction of those fractions. The common denominator is going to be 8 times 27 216. So 216, 8 minus 27. So we multiply um, this fraction by 8, and that gives us 8 over 216. This fraction is going to be multiplied by 27. So 27 over 216. And of course, that is negative 19 over 216. Okay, but then we got to multiply that by 3, the denominator, because that is those two fractions subtracted together. Of course, I'm missing the x cubed, which I'm going to apply soon. And then we're going to multiply by 1/3. So we're going to subtract 19 over, multiplying this, the denominator by 3 gives us 648 x cubed. So that comes from those two, and then multiplying by 1/3. Next, we have 4 over 9 x squared plus 4 over 9 x squared. I'm going to keep that paper handy. That's going to be my little computation paper. And where am I? Here. And then plus 16 over 3x plus 16 over 3x plus 64 over 3 with no x, close the parenthesis, dx. And then we combined like terms, of course. The highest exponent is cubed. So now we got to subtract 1/6 x cubed minus 19 over 648 x cubed. So I'm going to bring back my computations, little computations paper. So negative 1 over 6 and negative, and then we're going to subtract 19 over 648. So the common denominator, well, 6 goes into 648. 648 divided by 6 gives us 108. So we can simply multiply by 108, negative 108 over 648, and then keep the 19 there. So now we have the same common denominator, and that's going to give us negative 127, which is a prime number, over 648. Okay, so this integral is equal to 0.6 negative 127 over 648 x cubed. When you do your work for assessments in my classes, please do not use a graphing calculator to obtain the numbers. Just use a basic calculator like this one, and to obtain your results. Now, of course, when you're at home, after you finish this up, you can double check your answer by punching your original integral into a graphing calculator. That is okay. But for purposes of showing the work for the assessments, I do need to see your algebra, the algebra that is going to be part of the assessment, to make sure that you know how to handle those kind of situations. Those two are easier to add because we just multiply by 9 over 9. That's going to give us 36 nines plus 4 nines. That is 40 nines plus 40 over 9 x squared. So those two are taken care of. The cubes are taken care of. Plus 16 over 3x plus 64 over 3, close parenthesis. I'm going to put dx, and that goes there. Okay, so now we go back to one line, and then we attempt to finish this up. So, no integral anymore. This is negative 127 over 648. Okay, this is a regular polynomial. So when we find the antiderivative using the fundamental theorem of calculus to evaluate this integral, we are going to end up with a polynomial, and even the constant after you finding the antiderivative is going to have the variable x in it. So we're going to have this x. This one's going to have an x squared over 2. x cubed over 3, x to the 4 over 4. So when we plug in 0, all of those are going to become 0. So we're going to subtract 0 after we plug in the 6. Okay, so again, we're going to get 0 because this is going to be 64 over 3x, 16 over 3x squared over 2, and so forth. And when we plug in 0, we're going to obtain 0. Do take the time to think through that you're going to get 0. Okay. Once we know that, we could probably just, since this is a relatively simple thing to integrate, we can simply start integrating and plug in the 6. So this is going to be 6 to the 4 over 4 plus 40 over 9 times 6 cubed over 3 plus 16 over 3. And then we're going to have 6 squared over 2 plus 64 over 3 times 6. I don't know why there's no need to put the parentheses anymore, but since I open the parentheses, I'm going to close it. And then we're going to subtract 0. Yeah. So on your work, if you do something like that, that will be okay. What we don't want to do is take super short, or leaps rather, which a graphing calculator would be able to do, but this kind of calculator doesn't. Now, you don't have to have 2 calculators. You can simply stick with the white keys and those keys on the right, those number keys. Don't use the scientific area or the graphing calculator area, because that is the same. All right. And we want to end up with exact answers, which means we have to preserve the denominators. We have to preserve the fractions. Let's simplify 648. All right, so the 127 is a prime number, so I'm not going to be able to work with that. 4 times 648, I can just show you what I'm doing. 648 times 4 is equal to 2,592. Okay, 6 to the 4, so keep that in mind. 6 times equals, that's 1,296. That times 2 equals the 2,592, which is the denominator. So that means that this denominator is twice that 6 to the 4. So just divide by 2 when we simplify. So simplifying 6 to the 4 with that gives us just a 2 in the denominator. The 127 remains there. Yep. Plus 40 has 2's and 5's, so that doesn't simplify with this. 3 times 9 is 27. 6 cubed, let's see, 6 cubed is gonna cancel, so 40 times, and then we gotta figure out what 6 cubed over 9 times 3 will be, and I think that is 8, if I'm not mistaken. You can double check. 6 times, so that is 6 cubed, divide by 27, yep, 8. Plus, well, 16 over, well, there's many ways to do this. 3 times 2 is really 6. That cancels with one of the 6 there. So we had 16 times 6. Because the other 6, there's 2 6's here, but one of the 6's cancels off. So we have 6 times 6 is 36. We carry 3. 6 times 1 is 6. And the 3 carries 9. Plus, and then 6 and 3 simplified to 2. So we end up with 128. Okay, to make this easier on me as a fraction, I'm gonna, or as I'm adding those numbers together, I'm gonna turn this into a mixed fraction. So we have 60, because 12 divided by 2 is 6, 7 divided by 2 is 3, so there's a half left over, plus 320 plus 96 plus 128. Okay, so we have 128 plus 96 plus 320. But then we're going to take away, well, this is almost 64. So I'm going to take away 64, 480. But that I took too much off. I took a half extra if I took away 64. So the answer is 480 and 1/2. So that is, a geometric interpretation of this is that that is the volume of this thing. This is going up really, really high. I mean, this is x squared plus y squared. So by the time we get to, let's just understand what the outputs are. The output here is 0. The output here at 6,3, remember the function that we are integrating originally is x squared plus y squared. So we have 36 plus 9. 36 plus 9 is 45. So the output here is 45. The output here is 36 plus 36 is 72. And the output here is going to be 16. So, yeah. So as this height is 45, the height way up here is going to be 72. So we're talking about relatively large numbers. The area of this is, I didn't compute it ahead of time, but it is fairly large. It's somewhere in the neighborhood of 4 times 6, 20 or something like that. So 20, and then if this is, let's say, on average 30, we're going to talk about averages too. This is a fairly big volume. That's what I'm trying to say. The base is 20, 30. We're talking big numbers. So 600, for instance. So this number, I'm trying to justify that this number makes sense. 480 and 1/2 makes sense. This is an exact answer. All right, so that was just one example. The examples are getting longer in this multivariable calculus class. Okay. So now let's do example 2. And example 2 is going to be a redo of example 1 as an X variable boundary case. Whoa. So we're going to redo this, but seen from a different point of view. Okay, so our original region is this one. Yep, this one. And this goes from 4 to 3. So the height is changing. This is fixed. Now we want to see it this way. Now this picture is backward because typically the positive y-axis should be on the right. I didn't print another one of those. I should have printed another piece of graph paper so we can see the y on the right. But this picture is technically backwards, but it doesn't matter. We'll still be able to handle this. So remember, the positive y-axis is here. I'm not changing that. The positive y-axis was there anyhow. There's the y-axis, positive. The y numbers that are negative are down here, and these are the positive. So when I turn this picture around, the y-axis, the positive y-axis are on our left. Yep. And the positive x-axis is on the right. So from this perspective, well, this is, whoa. Yeah, we were integrating with a variable y. Now we want to integrate with a variable x. So the x varies from here to this point. We got to split this into 3 regions. Region 1, because the x varies on this interval from 0 to 3 on the y values. This is very, very confusing. From 0 to 3 on the y values, the 0 doesn't change and the 3 doesn't change. The y value is the same, but the x is changing. From 3 to 4, nothing is changing, so we're good. The boundaries are constant, flat, 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 flat. From here to here, again, the x is changing. So I'm going to label this region 2, the one in the middle, and this region is going to be region 3. So we're going to have region 1, 2, and 3. And you may be asking, wait a minute, why did you label that one as 1, 2, and 3? Why not from left to right? We go from away from 0. You know, when we're on the number line, you know, there is 0, and we count 1, 2, 3. So when we go away from 1, from 0, we start with a 1. Well, where is 0 here? 0 is there. So that's why I'm counting this as region 1, region 2, and region 3. I'm going to draw the picture, or attempt to draw the picture down here, because we're going to use it. This has a more gentle slope, and then this is shorter. This picture is misleading because it does look like a parallelogram. It is not a parallelogram. We go from 0 to 3, and that's going to be region 1. Then we go from 3 to 4. That's going to be region 2. Whoa. Nope, because that actually goes here. Bad picture. I got to get a new piece of paper. Oh. Yeah, so I'm going to try to draw. So gentle slope, straight, steeper slope. Yep, that's a little better. Region 1, region 2, region 3. The x value changes in region 3 and region 1. In region 2, that's pretty square. That's the easy one. That's a rectangle, as in the previous video. All right. Remember, this was and is y equals half x. That is the function f1. But because we're going to see things the other point of view, this is the same thing. If you have this equation, you can multiply both sides of the equation by 2 and solve for x. So that is the same thing as x equals 2y, and that is going to be G2. G2. No relation. I mean, there is a relation, but those are two different functions. So we're thinking of them as two different functions. G2 is x, which varies, and it will be 2y. So this is y. If this is very similar to what we did in Calculus 2, and we were integrating with respect to x or with respect to y. Here, there's no problem. Here, we're going to use this boundary, and this boundary was y equals third x plus 4. We're going to solve this equation for x, multiply by 3, you get 3y and 12, move the 12 over. So same thing as x being equal to 3y minus 12. So we're going to be using this and this instead of those two. Okay, so let's set it up. We have the integral, the double integral, over the total region. So R is going to be all of it. All of it is going to be R. So R equals R1 union R2 union R3. R1, R2, R3 of x squared plus y squared. Same function we did on example 1. dA. So this is a double integral with respect to the area, this area. we're going to break this up into three integrals. The first integral is going to go from 0 to 3. And I'm basing that on this picture, 0 to 3. That's where this point is. That's where this boundary stops being a boundary, and then we transition into this boundary instead. So we go from this boundary to this boundary, and that is the upper boundary. Upper means on this picture to the right. Yeah, again, you got to be careful with what we mean by up and down, because now yeah, it's like in space. And once you are floating in space, up and down don't make sense. You make up and down whatever you want them to be. So, yep. So we go from 0 to 3, 0 to 3, and then from 0, the 0 function, to a variable x, to y, x squared plus y squared. We're integrating with respect to x first, and then with respect to y, because y goes from 0 to 3. That's just for region 1. Then we got to add region 2. Region 2 starts at 3 and ends at 4. 3, 4. The x goes from 0 to 6. That's a 4. 0 to 6, x squared plus y squared, dx dy, plus the integral from 4 to 6, from 4 to 6. So you're thinking, well, there's nothing here. Yeah, because the lower boundary starts there, 3y minus 12. That's the lower boundary, 3y minus 12. And the top boundary is 6. Yeah. So it is interesting that those two lower boundaries are the same, because those two regions have the same lower boundary. Those two boundaries are the same for region 2 and region 3, because region 2 and region 3 have the same upper boundary. Now, I'm thinking of this. So up is on the right, and down is on the left from the perspective of the y values. I did not rotate the picture. If we rotate it, as I did here, and I meant the x values. So this is an x up and an x down. Yeah, if you rotate, this is the upper x value, and this is the lower. So those two are upper x value, and those two are the lower x values. And you may be thinking, whoa, this is way, way more complicated. Yes, we are making this complicated on purpose for two reasons. At least two reasons. The first one is we want to practice how to figure this out from the other perspective, from the XY perspective versus the YX perspective. So practice is the one reason why. Even though this is more work, it's just like when you are working out. What is more work, to lift weights or not to lift weights? Well, of course, it's more work to lift weights, but there's a purpose to it. Same thing here. This is more work than not doing it this way, but there's a purpose. We want to practice how to do this. We want to practice on the same example because we want to compare. And the other thing is, we should be asking ourselves, which one is easier, one or the other? Well, that varies depending on the shape. This shape was not conducive to this method. We're kind of forcing this method, the XY iteration, to work. We're forcing it. So after seeing this example, the end of this example, then we will realize that some problems are more suitable for one, the XY, dx, dy interaction versus the dy, dx interaction. And there's one other reason, there's at least two. We should obtain the same answer. we should obtain 480.5 because we are redoing the example. And the answer we got is still here, 480.5. 480.5 is the exact answer. Let me finish this up. X squared plus y squared plus dx dy. Okay, so the double integral got broken up into three integrals because this region is not suitable for x variable boundary case. It is not. We have to split it up into three subregions. Each one of them individually is suitable for either one of the two. Yeah. So because we're going to work with three pretty difficult integrals, I'm going to break this up into three cases. So I'm going to make this a little formal. Let A, B, C be the value of the three integrals above, respectively. If you're doing something like this in your work, if you're thinking, okay, I'm going to take this guy, do it by itself because this is just so big, I don't want to carry the other two with the computations, that's fine. Make it formal with a statement like this, please. And then you should be okay. So because I said respectively, this one is going to be A, this one is going to be B, this one is going to be C. So let's move on to, in that order, A. So now, okay, A is that integral. Let's copy down the integral first. So the integral from 0 to 3 of the integral, this is an iterated integral, 2y x squared plus y squared, close parenthesis, dx dy. Okay, so now we got an iterated integral to work on. This outer integral is going to wait while we figure out the first integral. The derivative, the antiderivative is going to be with respect to x, or the integral is with respect to x using the fundamental theorem of calculus, and then the antiderivative is going to be with respect to x. So we have x cubed over 3 plus, now that is a constant with respect to x. So we have x y squared as x goes from 0 to 2y. So this establishes where what we're gonna plug in. See, there's two variables, x and y, and we're gonna plug in 0 and 2y. 0 and 2y. So 0 and 2y are gonna go for what? For x or for y? And it could be either one because the two of them are present. But we're integrating with respect to x initially. So the x is the one that gets replaced. This x and this x. dy. So the outer integral waits while we plug in. So 2y here, 2y quantity cubed over 3 plus 2y times y squared minus 0 cubed over 3 minus 0 times y squared, close parenthesis, or oops, I started a bracket, so I better end with a bracket, dy. Okay. I typically don't write the zeros if I know in advance we're going to have a 0, but it is important in this particular example to show what we're plugging in. We're plugging in 0 for x, not for y. All right. I'm going to do two things at once. I hope I don't get confused. So 2 cubed is going to be 8. Keep the 3 there. And then we're going to plug in. So that's a constant, 8 over 3. And we're going to integrate. So we're going to have y to the 4 over 4. Y to the 4 over 4. Plus, that's going to be 2y cubed, which we're going to integrate with respect to y. So that's going to be 2y to the 4. Oh, this is a cubed and that is a cubed. I should have consolidated those two instead of integrating them. I didn't realize right now that this is a y cubed and that is a y cubed. I should have put them together ahead of time because we end up, this is silly, we're going to have y to the 4 twice. But anyway, 2y to the 4 over 4. Yeah, that makes sense because they came from a y cubed. And we're going to do that from 0 to 3. Yeah, I feel silly doing that because, yeah. Well, let's just finish up. This is a regular integral, calc 1 integral. If we plug in 0, we're going to end up with 0 and 0. So there's no point in plugging in 0 because that's going to go away. In fact, we can factor out the y to the 4 over 4. We plug in 3 in it, so that is going to be 81 over 4. So I'm just factoring out y to the 4 over 4, y to the 4 over 4. After we plug in the 3 into it, so that's y 3 to the 4 is 81. Factoring that out, so I have 2/3, rather 8/3, plus 2, because the 4 was already factored out, and 2 is the same thing as 6/3. So we have 14/3, 81 over 4 times 14/3. So the 81 and the 3 simplify down to 27, and 14 simplifies down to 7. But we still have a 27 times 7. Well, I can do that. 7 times 7 is 49. We carry 4. 7 times 2 is 14, 18 over 2. And that gives us 94.5. So half of 18 is 9. Half of 9 is 4.5. Okay, so that's A, 94.5. A equals 94.5. Out of the 3 integrals, we have knocked 1 down and we got 2 to go. Let's copy the second integral. So B, because we said back here that the integrals, those integrals are going to be A, B, C respectively. And we made it formal by writing a statement. Let A, B, C be the value of the 3 integrals above, those 3 immediately above, respectively, A, B, and C. Okay, so B is the integral from 3 to 4 of the integral from 0 to 6 of x squared plus y squared dx dy. So the outer integral from 3 to 4 is going to wait while we do the inner integral. The variable is x, so we have x cubed over 3, x cubed over 3 plus xy squared from 0 to 6. And then after we finish that, then we're going to do the integral with respect to y. So we're going to plug in, oh, it may be a good idea to emphasize that we're going to plug in x or 0 into x. So when we plug 0 into x, we're going to end up with 0 and 0. So we're going to subtract 0. So we can disregard that after double checking that we actually get 0. So we're going to plug in 6. We're going to have 6 cubed, which is going to be 216 divided by 3, 72. So we're going to end up with 72 integral from 3 to 4 of 72 plus plug in the 6 y squared dy. Okay, so that is 72 y plus 6y cubed over 3. Well, that is 2y cubed, because the over 3 cancels with the 6. And we're going to go from 3 to 4. So that is 72 times, plug in the 4, plug in the 3 into y, subtract, plus 2 times, plug in the 4, plug in the 3, subtract. So 4 minus 3 is 1, of course, so that is 72. Plus 2 times 64 minus 27. So 72 plus 2 times 14 minus 7, still 7. 5 minus 2 is 3. So I'm barely going to be able to fit it into this page. Plus 74. So that is 146. Okay, so far we got 94 and a half, 146 by itself, 2 down, 1 to go. This is going to be probably the most complicated one, because we have a variable lower limit and a constant that is not 0. Here we have a variable limit, which was actually nicer than this one, but we got 0. Zeros always help. 0, this one was the easiest one, but this one is going to be the big one. That was page 6 of my notes. So now we go into page 7 of my notes. All right, so now we go for C. We got A and B down, and now we go for C. C, I'm copying down, is the integral from 4 to 6, no zeros, so that complicates things. 3y minus 12 to 6 for the x's, x squared plus y squared, dx, dy. Yeah, that's going to be the big one. So we go from 4 to 6, and then integrate with respect to x. So we got x cubed over 3 plus xy squared. So it is the same. We have gotten the same thing on all a, b, and c, because it is the same function and starting with integrating with respect to x. But we're going to plug in different things now. 3y minus 12 to 6. And then after we finish that, then we're going to integrate that, whatever we obtain with respect to y. And we're going to plug in x, this into x. So we go from 4 to 6, and we have 3y minus 12 cubed. Oh, I just goofed that up on live video. The top goes first. So start all over. So 6 cubed over 3 plus 6y squared, 6y squared, yep, minus that quantity that I started writing down, quantity 3y minus 12 cubed over 3. And then this is getting too long for one line, minus quantity 3y minus 12y squared. Close the big parenthesis. I'm just double checking. 6, quantity cubed over 3, quantity times y squared, yep, dy. Okay. So 1, 6 simplifies with this, and we end up with 2. So we got 36 times 2, 72. 4 to 6, 72. Plus 6y squared. There's not much to do with that. Here, we can FOIL that out. Again, I'm using FOIL as a verb, but it's really multiply that out. Yeah, so let's multiply that out. But instead of multiplying that out, I'm going to simplify my I'm debating whether to multiply. Yeah, let's factor out a 3. If we factor out a 3 out of that binomial, the 3 factor out is going to be actually a 3 cubed. So that is going to be a 27. So we can factor out the 3 as a 27 because we're cubing the whole quantity. The 27 divided by 3 is going to give us 9. So minus 9. And then we have y minus 4 to cube. And y minus 4 to cube is a lot easier. So I'm going to show you here on my sheet of little computations, y minus 4 cubed. You probably want to pause because you want to multiply. I can just show you. So if you multiply 2 of those factors, there's 3 y minus 4. So if you multiply 2, you end up with y squared minus 8y plus 16. But then we got to multiply by y minus 4 one more time. And then we end up with y cubed minus 3 times 4 is 12, y squared plus 3 times 16 is 48, y, and then minus 64. So you, again, may want to pause the video to just make sure that you multiplying y minus 4 times y minus 4 gives you this. If you don't know that already, but you can take the time to figure that out. Once you have this, multiply with y minus 4 will give you that. So y cubed minus 12y squared plus 48y minus 64. Close the parenthesis, this parenthesis. We're not going to close this parenthesis yet because we still have to do this. Minus 3y cubed, double negative, plus 12y squared. Now we close this parenthesis and we got dy. Okay, so there's more to simplify. So that is the integral from 4 to 6. 72 is alone. So 72 is done. Those two are like terms, so we can consolidate them into 18y squared. And then let's distribute this. Minus 9y cubed plus 9 times 12, I believe is 108 y squared, minus 9 times 8 is 72. We carry 7. 9 times 4 is 36, and 7, 43. Y plus 9 times 4 is 36, carry 3. 9 times 6, 54, 57. That's a plus, 50. And then we still have to do minus 3y cubed, close parenthesis, dy. Boy, this is long, but that is C, it's the big one, remember? A and B were shorter. This has complications that A and B had. So we're still doing 4, 6. Y cubed, we got 9 and 3 both negative. So we start out with negative 12 y cubed. Y squared, now I'm going to consolidate the y squared. So we got 18 and 108, that is 126. Yep, plus 126 y squared. Negative 432 minus 432y. And those two are going to be 648 plus 648, no y, constant, dy. So finally, I was able to put this back into one line. We're integrating this polynomial with respect to y from 4 to 6. That's the page number 7. So page number 8. So now we integrate this negative 12y to the 4 over 4. So that is negative 3y to the 4 plus 126y cubed over 3. Well, 12 divided by 3 is 4. 6 divided by 3 is 2y cubed minus 432y squared over 2. So that is 216y squared plus 648y. And we're going to go from 4 to 6. Okay. So that is negative 3, 6 to the 4 minus 4 to the 4 plus 42, 6 cubed minus 4 cubed minus 216, 6 squared minus 4 squared plus 648, 6 minus 4. We're plugging in the 6, plugging in the 4. Since we have a product with a constant, there's no point in multiplying by the constant through. We can just wait until we do the subtraction by factoring. So 6 to the 4, where's my little calculator? We could do it by hand, but we are okay using this calculator. 6 times 2, 3, 4, 1,296 minus 4 to the 4. 4 times 2, 3, 4, 256 plus 42. That's got to be 216 if I'm not mistaken, minus 64. I better not risk it. 6 times, there we go, yeah, 216 minus 2136 minus 16, that one I do know, plus 648 times 2. 6 minus 4 is 2, so that is negative 3 times 6 minus 6 is 0, 9 minus 5 is 4, 12 minus 2, I missed the 0, there you go, 10. 1040 plus 42 times 6 minus 4 is 2, 15 minus 21 times 20, and we can already do that, plus 1296. So that is negative 3,120 plus 42 times 152 is 6,384 minus, that's 420 plus 1296. So 6,384 is here. Let's add 1296 minus 3,120 minus 420. That's going to be too big of a number. I made a mistake. I'm going to pause the video for a moment so I can find the mistake. I found a mistake. It was a sort of a typo. Here we have 216. And then when I copy this, there's the 42. I copied here as 21. So I was missing a 6. I'm going to use a different color. So I was missing here a 6. 216. And I was missing a 6 here. 216. So 216 times 20, that is 432. I'm just gonna So this is 4320. So we're subtracting 4,000. Okay, so let's start all over with this addition. 6384, 6384 plus 1296, 1296 minus 3120, 3120 minus this number 4320, 4320, and that gives us 240. 240 exactly. Okay, so that's C. Remember, C started out on page 7. This is my page 8. You don't necessarily have to have the same pages, of course, because you're taking notes, and but A and B. So A, let's put a division here. So A, remember from before, was 94 and a half, 94 and a half. B is 146, and C is 240. We add all of that together, so we end up with a half. 4 and 6 is 10. We carry 1, 10, 18, carry 1, and sure enough, we get 480, which is exactly the same answer we got in example 1. We were supposed to have the same exact answer. So in example 1, we figure out the double integral of this total region in one shot, in one integral, double integral. In example 2, we redid the problem, but now we had to split it up into 3 different regions. And that took way, way more work. However, when we put them back together, we should end up with the same answer. And we did. This is these problems do take a long time. So some students, when they are doing multivariable calculus problems, they say, boy, it took me a half an hour to an hour to do one single problem. And my reply to that is, you are doing good. You're actually doing very well if it only takes you half an hour to an hour. Sometimes it takes me longer to do one problem. When, again, I'm going to repeat, when you are doing integration in my classes, do not use a graphing calculator to find the integrals. You could, to check your answer, of course. And I would definitely do that if I was you. I would definitely use that. But I need to see your algebra, because that is part of what I'm assessing in this class. All right, we're going to stop here.